Welcome everybody. Good day, good evening. This is August 3rd, and this is the third in a series of 6 classes on science from the Lyndon LaRouche standpoint. Today we will be examining the work of Pierre de Fermat. He is a truly amazing man who is very underappreciated, if you ask me. And his discoveries span many fields. The one that we're going to be focusing on today is the principle of least time for light. How is it that light bends when it goes from one substance into another? What explains this? That's what we'll be looking at. I noticed that also I'll remark I had sent out an introductory video that gives an overview of this. Somebody wrote back that it was enlightening. Thank you, Hugh. So let me start with the phenomenon in question. Let's take a look at light refraction. So I'm going to use my camera here. Okay. And Mike, could you allow it to, oh, here. I'm just going to pin this other one for now. Good. All right, so you can see here, people here aren't going to be able to see it unless you... Good, here we go. All right, so what you're seeing here, maybe it's a little hard to see what's going on. There's we've got a lens. This is just a piece of acrylic. I've got a piece of paper with the slit cut in it, and I've got my, phone flashlight. So what we're seeing here is here we've got light going through the lens. And at this angle, when the light's coming in, at a 90-degree angle to the lens, the light comes through straight. Nothing unusual happens. If I move my light to the side, you can see there's a difference, isn't there? So what we're seeing here is you're seeing, hard to point to. This is the straight path. This is supposed, like, see, this is the direction that light was coming into the lens at, but over here you see the light that's actually coming through the lens. So let's take a look at that as I move this around a bit.
I'm sorry, you said the one on the paper is going through the lens and the other one is what?
Is if it were going straight. So the one that's closer to the center, that's the straight path of light. But the light that actually comes through the lens is over here, is this one. This is if it went straight, but this is what happens. The lens is causing the path of light to bend. And you see the difference gets bigger if I'm over here on the side. When I'm in the middle, there's no difference. One other thing to do is to look at light going the other way. I have to turn this around. So you can see the light's coming through the lens, and you can see how the angle is different on the non-lens side. How would you say that it's different? What's happening to the angle in this case? Is it I'm sorry, when the light goes through the lens, how has its path changed?
Extreme.
More extreme, yes. So measured with respect to this, with going straight, it's more extreme over there. And if we go a little far
It
enough,
also seems to be bending away from the source.
So we if we come far enough, light is not coming through anymore at all.
It's refracting.
Well, what it's starting to do is it's starting to reflect. You can see it's starting to come across here. It's staying on this side. The lens, the flat side of the lens here is acting like a mirror when we're at these angles way over here. When we come closer to the middle, then the light can start coming through. So this is the phenomenon of refraction. This is what we're going to be taking a look at and figuring out today. Okay, so just to jump right into where people figured this out. This was a problem that puzzled people for a long a long time. I'm sorry. Okay. Just keeping an eye on the chats too. This was a problem for a long time. People knew that it came up, for example, in astronomy. When you see a star that's way up in the sky versus when it's down near the horizon, do you know how being near the horizon affects the perceived location of a star? So I don't know how the light bends as it's going through the atmosphere more as opposed to just basically going out of it.
Makes it look bigger?
I think it makes it look higher. It looks further from the horizon than it would be if there were no atmosphere. Now, exactly how much different it is, this is something that Kepler takes up in the book that we were looking at last week to try to figure out how much does light bend. But no one figured it out until in 1637, I believe, René Descartes published a book that gave a formula for how light bends. And we're going to see what his argument was, what Fermat thought about it, and then what Fermat said was the real reason for light bending. But I realized I wanted to start by reading this from the reading packet, the opening quote from Lyndon LaRouche. And given the length of it, I think we'll have two readers. And as I often do, if you are on Zoom, I'd like to give you first dibs. So would anybody on Zoom like to read this? I'll put it up on the screen. Any Zoom hands raised?
Well, if you put it up on the screen, I will read it.
Okay. Well, I believe it is up. Can you see it?
Yes, I can. So,
Take it away.
my included purpose in the immediate project on animations is to demonstrate to intelligent professionals and to others the proper methods of approach in use of computerized animations of county-by-county data that over periods of 2 or 3 generations in showing the determining factors in cause of catastrophe or recovery in the US economy in particular today. This work is premised at its first stages on the way in which Johannes Kepler defines cycles within the solar system, and the way in which Kepler thus defined the need for developing both the infinitesimal calculus, uniquely developed by Gottfried Leibniz, and the successive development of elliptical and higher hypergeometric functions by Gauss, Abel, Riemann, et al. The crucial topics treated under that approach include the functionally determined relationship between the general basic economic infrastructure of whole economies and the productivity of agriculture, manufacturing, and rates of tangible physical growth in the so-called private sector of an economy taken as a unified whole. However, the crucially underlying objective of these studies is to discover the principal factors which are determining or might determine either net growth, decline, or stagnation in the rate of the performance of the economic phase space considered, or a national or larger economy as a whole. The most suitable pedagogical approach to this crucial feature of the study is that modeled on the most essential distinctions of Kepler's reference discovery, the discovery of the principle of the infinitesimal. This is the distinction which is apparently beyond the comprehension of today's commonly encountered academic classroom and related productions respecting the principles of physical, scientific, and related investigations. Kepler and spherics. Knowledge is always essentially subjective because it exists among mortal beings only as human knowledge. Its primary existence lies consequently only within the human individual and that individual's functional relationship to the history of the society within which he or she lives. Knowledge, in the proper sense of the word, does not exist among lower forms of life. Knowledge is an attribute of that principle of the human individual which sets our species absolutely apart from both inanimate objects and also all lower forms of life. In V.I. Vernadsky's Science of Biogeochemistry, this marks the principle which separates the human individual from the animal. This is the standpoint from which to consider the rudiments of the method employed by Kepler. This is the standpoint plausibly attributed to the work in astronomy of Thales of Miletus, and is the standpoint of the Aristarchus of Samos, who proved the orbiting of the Earth around the Sun by appropriate experimental methods. Kepler's treatment of the relative positions and motions of solar bodies considered by him can be traced from the starting point referenced by Aristarchus's approach. Also, as Kepler himself emphasized, his own scientific method was derived from the founding of modern physical science as an experimental body of scientific work by Nicholas of Cusa, and as Cusa's initiatives were complemented by the work of such followers of Cusa and predecessors of Kepler as Luca Pacioli and Leonardo da Vinci. That much said, it is sufficient for the purposes of the present report to focus on a narrow but crucial feature of Kepler's discoveries, the implications of the observed Mars orbit in terms of reference to the cyclical alignment of relations among the positions of the Sun, Earth, and Mars. To reduce the matter to essentials, we may say the generation of an elliptical orbit of Mars was recognized by Kepler's measurements to be the result of what Gottfried Leibniz was to make his unique discovery, his definition of the differential of the infinitesimal calculus. Simply said, the notion of the infinitesimal, which Kepler presented to future mathematicians, was a reflection of the observed consistency of the fact that the area subtended by the sweep of the orbit of Mars relative to the Sun varied in an ordering of equal areas swept during equal times. In other words, the elliptical orbit did not determine the motion of Mars. Rather, the relevant, perfectly infinitesimal principle of physical action generated the elliptical orbit of this specific characteristic, the characteristic of equal areas swept within equal times.
Good. Let's take a moment here to discuss what we just had. Also, I got to ask you, Hugh, do you work for Audible or do you do LibriVox books? Because it was a pleasure to hear you read.
Well, actually, I do some reading for. We have an organization up here that follows the LaRouche organization called Canadian Patriot, and I've done some. I did a book for them. I did an audio book for them, and then I've also done some other narrations for them.
Okay. All right. Well, sounds good. So let's take a moment to think about what we've just read. We have not mentioned Fermat so far, but we've had a fair amount about Kepler. Would anyone like to? Does this make any different kind of meaning in your mind based on the class and the discussion on Wednesday for those who are able to make it? For example, when LaRouche says that the elliptical orbit doesn't determine the motion of Mars. The orbit doesn't determine the motion. But the relevant perfectly infinitesimal principle of physical action generates the elliptical orbit. If there are any reflections, please feel free to share. And if not, that's okay too. Anyone have anything they want to say about what we've read so far? Kepler?
I find it's a little hard to get my head around.
Okay.
Jason,
Roger.
Jason. Yeah, the only thing I'll say quickly is it's very easy for people to say, well, okay, it's not a circle, but an ellipse, that's another conic section. It's another regular figure. But when you think about the fact that there's nothing that requires it to be a regular figure, a conic section, or anything else, that at every single instant, the interaction of the planet and the sun, and actually the other planets as well, just happens to be generating that particular curve. And as we saw from last week's class, he went through many approximations in order to convince himself that it actually was an ellipse and nothing else that might approximate one. So I think that's the idea of the infinitesimal, that at every instant the orbit is being created. There's no guardrails that are pre-existing to guide the planet on any particular orbit.
Hmm. I like that image of not having guardrails. Um, so I like that image of not having guardrails, that the orbit isn't being, Mars isn't being, pushed into an orbit by something, pushed into a motion by something that exists out there. It's doing its thing, and the result is this ellipse. So we had, on Sunday, we had Kepler's hypothesis that the speed of a planet is determined by how close it is to the sun. That the reason he says planets go around the sun isn't just because it makes the geometry simpler or it's a nicer model. He said, well, the reason that planets go around the sun is because their motion is determined by the sun. It's not just sitting at the middle of the orbit, it's causing the motions. And then on Wednesday, we saw a little bit more about how Kepler understands the distance of the planet from the sun. So if you missed Wednesday, and I know most people did, we kind of went into that there. The result of the two put together ends up creating an ellipse as a result, not as a shape, not as a conic section. Yes, and then we'll keep going. Yes.
I'm not quite sure how. Seeing the idea of an elliptical orbit with the concept of equal areas and equal times determining the orbit. Where did that come from?
So equal areas and equal time comes from what we ended with last Sunday, which is that, so Kepler is saying, okay, if the speed of a planet is inverse to how far it is from the sun, turn it the other way. Based on how far you are from the sun, that determines your time per degree of motion. If you're further from the sun, it'll take you longer to move the same amount. If you're close to the sun, the amount of time for that same motion will be less. So Kepler's saying, well, what does that mean over time? So, here's the sun, here's the planet's over here, here, here. It keeps changing its distance from the sun. Here it's slower. As it comes over here, it's a little closer to the sun, it's faster. So what he says is, what's very similar to that is if I drew all of these lines from the planet to the sun, the sum of all of those lengths would tell me how long it took the planet to move. And he says a bunch of lines from the sun to all the positions of the planet, if you kept drawing all these lines, it's sort of like coloring in the area that the planet sweeps out. So there's more to it, but he uses the area. Kepler's real belief is that the distance varies with the speed from the sun. The area time is sort of a result of that. But
Okay.
yeah,
No. Lynn is saying that the,
yes, yes. Kepler thinks about equal area, equal time much earlier in the book, but it's a hypothesis. He's not really sure about it, and he doesn't really like it. It's not until his later book, The Epitome of Copernican Astronomy, that he really is at peace with the idea of the area measuring the time. And I'm not going to go into the details of why, but that's where he comes to his peace with that. Yeah.
The idea what Art was asking, is it comparable to, say, an ice skater who is turning around very quickly and then retracting the arms and then starting to turn faster because of that, or then placing the weight
more further from the center of rotation? Would that be
a valid like alternative to looking at this model, like an alternative to angles and geometry, which
yield the
sort of the same result?
Hmm. Yeah, perfect. Yeah, yes, basically it's the same thing. So, you know, the ice skater pulling their arms in, they go faster. That's very similar. It's essentially almost exactly the same as the planet when it's closer to the sun, it goes around faster. So that's a really good image. Okay. Let's keep going on this because we want to get to the main course, so to speak, Fermat. So we had a reader from Zoom before, so let's take a reader from the room here as we continue from the bottom of page 2 in the handout, bottom left. Volunteer. No, we got a tough act to follow after Hugh, but okay. All right, Jose, go for it.
Notably, precisely that view of the matter by Kepler prompted him to assign the future mathematicians the development of both an explicitly infinitesimal calculus and of a corollary theory of physical elliptical functions. The former challenge was solved by the uniquely original discovery of a calculus of the infinitesimal by Gottfried Leibniz. The quality of the calculus, which is projected in the failed attempt to understand gravitation by Isaac Newton and his followers. The second challenge of discovering the relevant physical principle underlying regular elliptical action was mastered in essentials by Carl F. Gauss and his followers, most notably by Bernard Riemann, who followed Gauss in going beyond elliptical functions into higher physical hypergeometries associated with an ontological insight into the matter of the human species' qualitative progress. The actual rudimentary development of the mathematics of a competent mode in modern physical science was derived entirely from the combined effect of these implications of Kepler's discovery with what Gauss was to expose as the implication of what was actually Napier's definition of the pentagramma mirificum, and Fermat's experimental demonstration of the existence of physically relative time. The concept of quickest time, as opposed to primitive superstitious belief in simple Euclidean, example given in Euclidean time. These are the elementary considerations, as treated most notably by Leibniz, Gauss, and Riemann, required for the defining of a competent modern science of physical economy. However, in any competent science of economy, there is another crucial aspect to Kepler's uniquely original discovery of universal gravitation. This is what William Nordhaus's treatment overlooks completely. Kepler's discovery of the principled ontological character of the planetary orbit provides students the model of reference for study of economic cycles. However, in any competent science of economy, there is another crucial aspect to Kepler's uniquely original discovery of universal gravitation. This is what William Nordhaus's treatment overlooks completely. Kepler's discovery of the principal ontological character of the planetary orbit provides students the model of reference for study of economic cycles.
Good. Thank you. Thank you. So now let's jump back into what Fermat did. And I'll start by showing a schematic here of the refraction of light. And then we'll talk about what makes it happen. Here we go. All right. So here's a very simplified view of refraction. So the upper part of this is air, the lower part is water, so to speak. So there's a few different lines that we're seeing here. The orange line below in the lower part of the figure, this is if the light went straight. Of course, it doesn't. It bent when it entered the water. Now it's moving along this blue line. The question of what is the relationship between the angle up top, how far we are away from the perpendicular up top, and the angle below, how far away are we from being perpendicular in the motion in the new medium?
I don't think I understood that. What do you mean from up top?
So So this is our flashlight. We're able to put it wherever we like.
Okay.
If we put it right here, so that the light is hitting the boundary of the new medium perpendicularly, its path doesn't change.
Right.
It looks like it just goes straight.
Yeah.
So the question is, as we move further away,
Okay.
like let's say here we're about like 45 degrees.
Yeah.
We've moved a half of a right angle.
Oh, yes.
So up here we have 45 degrees. Question is down here, what do we have?
Oh.
How far away did the light move from being perpendicular in the new medium?
Okay. Thank you for explaining it like I'm 6.
Okay,
No, it helps.
okay. I thought you were supposed to do it like someone's 5, but it's a little too advanced. All right. So, also let me see if this works. Oh, no, it doesn't. It would have been really nice to be able to. Oh yeah, okay, here we go. And then if we put the light originally, if we put the light underneath, this is what we saw before. When the light is going through the water, or in our case, that plastic lens, it reflects. It totally reflects until you reach a certain angle, and then it starts to actually pass through it. So we saw this phenomenon also, that when the light starts in this case, denser medium, water or the acrylic lens, there's some angle beyond which the light it can't get through, and it starts to just completely reflect. It always reflected a little bit, but at this point it's all reflecting. And you see this if you like to go swimming. If you're underwater in a pool, if you look straight up, you can see the sky or the roof of the gym or whatever. But if you look a little bit at more of an angle, you look further along the pool when you're underwater, you end up seeing the bottom of the pool. So that's an example of
When you're looking up.
yeah, so like if you went down to you're sitting on the bottom of the pool and you're looking straight up, you'll see the roof. But if you look further, like halfway down the lane, you're going to see the bottom of the pool. It'll reflect. Exactly. Yeah. So the question is, how do we explain these things? Why is there this weird angle where it doesn't go through anymore? And why? Because we're cuckoo. Okay, that's quite an answer. So Roger Ham says, what determines that angle? Perfect. Very good question. So Descartes won the prize for being the first person to publish a book that gave a formula. And he did this in 1637. What he said is that, take a look at the horizontal lines on this diagram. This horizontal line is a kind of a measure of how far away we are from being perpendicular, right? It's saying how far to the side are we instead of being straight up and down. Here's what Descartes wrote. He said the ratio of this line in one medium to that line in the other medium, it's a constant ratio. For the case of air and water, it's almost exactly 4:3. That is, if you took this line, cut it up into 4 pieces, took 3 of those pieces,
It would fit this horizontal.
it'll fit there perfectly.
Okay.
Perfectly. And let's try this in a few different spots, like over here when we're almost at the bottom, right? So this would be the full radius. The question is so this should be about 3/4 of the radius. Let's bring this line up here. Yeah, that seems reasonable. We've got 1 on this side and 3 on this side. You don't know anything from looking at it, but it's consistent with this hypothesis. We don't know it by, as we saw last week and heard from Adrian, and he showed us that just because it matches what you see doesn't mean for sure that it's right. But Descartes was pretty happy with this because everyone said, wow, Descartes' right. This tells us now we know the angle. And indeed, it's great now that we actually know the angle.
But it doesn't tell you why.
No, but so that's why we'll now read Descartes and we'll find out why. Because you're right. Why does that angle, why does this relationship happen?
Because if you can, it's one thing to describe what you see, which can be useful, but like why?
Yeah.
Right? So,
Oh, let me do one more thing. I want to express this in another way. The way that you would have seen this in a physics book when they describe this as Snell's law, and more later on why we call it Snell's law, is that this horizontal line up here, this is the sine of this angle. It's called the angle of incidence in a physics textbook.
Okay.
And so the sine is the opposite side on the triangle here. The hypotenuse is the radius. And then down here, similar thing. This angle of refraction, its sine is this blue horizontal line. So it gets expressed that the sine of the index of the sine of the angle of incidence is in a constant proportion to the sine of the angle of refraction. That's Snell's law. Okay, so yes.
Question that maybe we won't talk about it here, but just for people to think about is that you said that if there's no change of medium, light goes straight. And the question is, how do you know that, and what does that actually mean?
Oh, okay, good. I don't know if everyone heard that, so let me just repeat that. I know there's a lot of audio switching that has to happen to make this work. Adrian said that the claim was that if light stays in one medium, it goes straight. How do you know that? How do you measure whether it's actually straight? Fantastic question. Yeah, the idea, what Descartes would say is if you're in the same medium, it always goes straight.
So
But
like if you were in water to water, it would go straight.
yeah, or like if you're just staying in, well, in other words, you put a laser pointer underwater, it goes straight in the water. You put it in the air, it goes straight in the air. Question, how do you know whether something's moving in a straight line? What is a straight line? This isn't the easiest question, to be honest. Say a couple of questions. What is the purpose of knowing this? From two people in the chat. Well, the purpose of knowing things is to better understand the universe. This in particular has got applications, like I'd said, in astronomy. It's got applications if you're making lenses, you want to make a microscope, you want to make a telescope. You need to be able to understand how does the light bend as it's moving through the different lenses that make that up. When you're designing a smartphone camera, there's a lens there, and you have to know how does the light path change as it goes through these lenses to be able to design these kinds of things. So those are some of the really fiber optics rely on the principle of that critical angle where you get total reflection so that the light is not leaking out of a fiber optic cable. Those are a few specific applications. The importance of that this has for science more generally, we haven't come to yet, because that'll only come when we get Fermat's idea of why it's happening. So far, it's just something that you might have observed and noted. The question is, why? I hope that helps, and thank you for posting things in the chat, and keep it up. I'm keeping an eye on it as best I can. So let's switch and see why. The question we always want to know, why? So this is from page 6 on the handout. I'll put it up on the screen here. And I think it is time for a, oh good, glad that helped. It's time for someone on Zoom. If we have anybody who would like to raise their hand to read Descartes. No French accent required. Nobody wants to be Descartes. Oh, Joe Jennings raises his hand. Thank you for your sacrifice. Go for it.
Okay. First discourse on light. Now, having no other occasion to speak of light here, except to explain how its rays enter the eye and how they can be deflected by the various bodies they encounter, there is no need for me to attempt to say that what light's true nature is. And I believe that it will suffice for me to make use of 2 or 3 comparisons which aid in conceiving it in the manner which seems to me the most correct to explain all of its properties that experience has made known to us, and then to deduce all the other properties which cannot so easily be observed. In this, I will be imitating the astronomers who, although their assumptions be almost all false or uncertain, yet, because they agree with many observations that they have made, nonetheless allow the derivation of many very true and quite certain consequences.
So we definitely have to pause there.
Okay.
There is something very wrong with this. Okay, I agree. What would Kepler, in fact, what did Kepler have to say about this? Remember, this book is written 30 years after the one that we read last week, The New Astronomy. What do you think about Descartes' view of what astronomers have as their goal? Any thoughts?
Well, he says he doesn't have to say what light's true nature is, right? So
could you,
And
maybe
also,
that's a little too precious to understand. Well, could you, I don't know what you mean.
and also,
Reality is just
and also,
If the end result, okay, yeah. Well, look, what's Descartes saying here? He's saying, okay, astronomers, even if everything they think is actually wrong, yet because they agree with many observations, they're still helpful. Descartes is saying astronomers don't know why the planets move. Their only standard is, does their formula, does their hypothesis tell you where you're going to see that red dot in the sky in 2 months? Pathetic, right? This is Kepler showed that this was totally wrong. Okay, Joe, why don't you continue here?
Well, we talked about, William of Occam's razor, right? You just looking at discrete phenomenon, but you don't have to worry yourself with causality, right? So do you want the footnote, Jason, or not?
We'll leave that for people to enjoy on their own.
Okay. Now we come to refraction. And first, let us suppose that a ball impelled from A toward B intersects at point B, no longer the surface of the Earth, but rather a cloth, CBE, which is weak enough that the ball has the force to break it and pass through it while losing some part of its speed, 1/2, for example. Now, under this hypothesis, in order to know which path it must follow, let us again consider that its moment differs entirely from its determination to move in one direction rather than another, from which it follows that their quantities must be examined separately. And let us consider that of the two parts of which one might imagine this determination is composed, it is only that which makes the ball move downward that can be changed in some way by the encounter with the cloth, while the determination that makes it tend to the right must remain the same, since the cloth is in no way opposed to motion in this direction.
So just, isn't it, if you think it's kind of strange that there's a little picture of a man with a tennis racket and we're hitting balls through cloths as a way of explaining light, you're not alone. This is strange. So trust your instinct on that. Just to sort of restate what he said. So here's light, a ball, it's going from A to B. And then Descartes said, let's say that when it cuts through, breaks through this cloth here, it tears it, and it loses half of its speed. When Descartes says the determination that makes it go to the right must remain the same, he's saying that after the ball breaks through this cloth and loses half of its speed, it won't lose any of its speed to the right. Only its downward speed will change. Because if the ball was just moving to the right, it never would have touched the cloth.
Oh.
So therefore, the cloth doesn't mind motion to the right. So even if you do hit the cloth and rip through it, there will be no change in your motion to the right, only your downward motion.
Is it like thinking in vectors? Like sort of this old-fashioned.
Yeah, it sort of is. But his physical hypothesis is this one that only the downward motion changes. So, okay,
a miraculous
let's
cloth of
keep
zero
reading.
thickness.
Oh, Kevin's speaking, and we didn't hear him. Oops. Kevin, are you saying something?
Among other miraculous things, it is a miraculous cloth of zero thickness.
Yes. All right, since you're unmuted, would you like to continue the reading, Kevin?
Sure. I had stepped away, so I wasn't looking, but I was listening. So where are we?
We're right here on the screen, right below the
Okay.
first picture on page 7.
Sure. Then, having described the circle AFD around center B, and having drawn at right angles to CBE, the lines AC, HB, FE, such that there be twice as much distance between FE and HB as between HB and AC, we will see that this ball must tend toward point I on line FE. For since it loses half its speed in passing through the cloth CBE, it must take twice as much time to descend from point B to a point on the circumference of the circle AFD, not to be confused with AFD, as it took above to go from A to B. But as it loses none of its determination to move toward the right in twice the time that it took to pass from line AC to line HB, it must go twice the distance in this same direction, and consequently arrive at some point on the line FE at the same moment that it also reaches a point on the circumference of the circle AFD, which is only possible if it goes toward I, since it is the only point below the cloth CBE where the circle AFD and the straight line FE intersect.
Okay. So that's Descartes' reasoning that if the ball loses half of its speed, it'll end up here at point I. It moves twice as far to the right as it did before breaking through the cloth. This is twice as much as this distance, because since its speed was cut in half, it'll take it twice as long to reach the circle. And in that time, it will have gone twice as far to the right, and therefore this is where the ball will go. How does that square with what we saw about the refraction of light when it went from air into water, which seems more difficult to move through? Is this what we saw?
No.
No? What's different?
Angle refracted the other direction.
It's bending the wrong way. Yes.
What do you mean? Say that again.
Well, let's
You
take
were spearfishing and aim at the fish. You miss it by a mile. Because he's saying that the light is going up and to the right when it's actually going down.
Let's compare. So this is reality. Well, it's a it's an image that animates a understanding of reality. And you can see where which way the light bends. Compare that to what Descartes has in his picture.
This is going up instead of down.
And it's bending the wrong way.
Mm-hmm.
Denise asked, did Descartes actually do this or just assume this? No, he really did not actually do this with putting balls through claws. And so if he had, he would have realized that this is wrong. This is actually a common theme in Descartes' physics work. He also wrote some laws about collisions, about how things bumping into each other and what will the result be, how much of the motion of the moving thing is given to the one that was stationary and all this. Leibniz proves that among Descartes' laws of motion, every single one was wrong. Two completely identical things moving at exactly the same speed will bounce back away from each other at the exact same speed. That's the only one Descartes got right. So no, he was a little full of himself, Descartes was. So
we
thought,
can give him credit for consistency.
if it makes sense to me, it's probably right because I'm Descartes. So good question there.
He obviously never
Denise. Who must not have done physical things. So let's take a look. Let's continue and see how he explained, because obviously, the light's bending the wrong way here with this explanation. So instead, I guess the light better speed up to make it bend is the way that we see in the diagram on the right. So I'd like to have a new reader. Let's have someone in the room here for this time to read here from pages, it says 18 to 19.
Oh.
Anyone in the room, please?
I can read.
Go for it.
Oh, no, go ahead. But let us make yet another assumption here, and let us consider that the ball, having first been impelled from A toward B, is impelled anew, once at point B, by the racket CBE, which increases the force of its movement by, for example, a third, such that it afterwards traverses the same distance in 2 moments of time that it earlier traversed in 3, which will have the same effect as if it encountered at point B a body of such a nature that it passed through the surface CBE a third more easily than through air.
Okay. So what explains light speeding up when it goes into water? What is Descartes' physical image here?
There's a racket at CBE that increases the force of its movement by a third.
Yes. When light hits water,
It gets
a racket smacks it down, and that's why it goes more vertically in the water. He really wrote this, okay?
What racket?
He's got a racket, doesn't he? Yeah, there's no, right. So he's just saying, remember what he said before. It doesn't matter if your assumptions are false or uncertain, as long as they match reality. So he's really, he's cutting himself some slack here. He's being kind to himself. He's saying, hey, if it gives me the right angle in the end, why not?
So God doesn't shoot pool, but he does play tennis. Huh?
Or is this just like
No.
It's an analogy.
You're right.
But he's saying, he said in that very first excerpt, I'm not going to tell you what light is. I'm going to use some analogies so that we get the right conclusions. So he's really not worried. He does say that there's not really a racket. What he says is that it's so much easier to move through water that it will naturally speed up when it gets to the water. Because we all know it's much easier to move through water than air, right? What are some things that move more easily through water than through air? People? Okay, a fish. Unless maybe a flying fish, huh? And okay. All right, good point. Good point. Fish do move faster in water. But like, tennis balls, they definitely don't. You throw a ball at some water, when it hits it doesn't speed up when it enters the lake. It slows down. But that won't bother Descartes too much. So that's enough of him. Let's take a look at, there's some questions that came in. So before we continue reading and get Fermat's response to this brilliant remark from Descartes, let me see here. So Milton from Brazil writes, I'm not sure if the question about identifying the cause of motions was directed at me, but I'd still like to offer my opinion. I view the allegory of the cave as a question of who can see the light outside the cave and who cannot. Knowledge would be that light. However, in the same book by Plato, there are sophists as well as philosophers, and the concept of a republic involves searching for the truth. This is why I asked about emotions as a means of controlling this battle, not for those who do not see the light, but for those who have seen it and wish to manipulate the truth itself, the sophists. I think I must have missed an earlier message. Okay, earlier message from Milton. Could the battle between light and perception of reality be a dispute over emotional control? Is knowledge the light that illuminates our feelings? What is the emotional reason for promoting Descartes? It's a good question. Michael says that sound is faster in water than in air. Yes, that is true. That's why when you're underwater, you can't tell where a noise is coming from. It hits both of your ears. We have 2 ears, so we can tell which ear hears the sound first and get a sense of where it came from. But in water, the sound moves so fast that you don't know where it's coming from. Julian, how is the infinitesimal a principle when, as I understood how you, Jason, used it, was talking about Kepler noting a planet's position in its orbit, shown as an ellipse. But the real principal discovery that is seen with the mind, not the senses, is universal gravitation. If I'm mistaken, please explain the infinitesimal as a principle. Okay, yeah, let's say a bit about this and then we'll see how Fermat responded to Descartes. So oh, you're saying that one?
Go ahead.
Okay. Yeah, so although the planets move in ellipses for Kepler, the idea that's causing their motion is one that changes every moment. Because the planet's distance from the sun is always different, they don't move in circles, at every moment of its motion, its speed is changing. So even if you wanted to break up the planet's motion and say, okay, let me see how far it moves in one day, the speed that you calculated at the beginning of that day to see how far the planet moves, it won't be right during that day. Because let's say the planet's getting a little closer to the sun during that. Every hour it's getting closer to the sun. Every hour you could say, oh, this is the speed. Let's use this speed for the next hour. But even during an hour, it's changing. Should you use a minute? Should you use a second? The brilliance of the infinitesimal is to bring that time down, not literally to nothing, but to something that's infinitesimal, that's smaller than any finite number, and represents not an actual amount of time, but a change.
Yeah,
I wanted to ask, would it be easier to think about it as like the
first derivation, or like the rate of change, if you would say I'm driving like 90 miles an hour. So that would be an infinitesimal thing, like that would be a thing that is constant. Would that be helpful?
Yeah, okay. So what Martin is asking, is this like the first differential? The speed, if you're moving at some number of miles per hour, well, that's the speed at each moment. You don't have to wait an hour to say, okay, I went 60 miles in 1 hour. You say, right now, that's my speed. So if we imagined a tiny period of time, my speed, my distance traversed divided by that time would be this speed. So yes, that's exactly right. The infinitesimal is the differential. It's the rate of change, the kind of change. So the idea is to understand phenomena, not in terms of how they appear, not perceptually, but as what was making them happen. So like when you see things in an economy, think about what made them happen. You see some object, what goes into making it? You see some infrastructure. Where did that come from? What kind of thinking, what kind of social approach results in that? You want to start thinking about economic infinitesimals. What's driving the change in human economy as we move forward? Okay, let us return. Let's get to meet Pierre Fermat and see what he thinks about Descartes' absolutely brilliant reasoning. And I think it's where we had Kynan last. Oh yeah, so it's someone on Zoom, please. Would anyone like to volunteer to read this letter from Fermat to Mersenne on the top of page 8 of the handout? Please raise your hand or just unmute.
I'll read, Jason.
Okay, great. Thank you.
Yes, Julian. All right. You asked my views on the treatise of dioptrics by Descartes. This is his argument, more or less. Light is nothing other than the inclination of luminous bodies to move, and this inclination toward movement must probably follow the same laws as movement itself. And it follows that we can establish the effects of light based on the knowledge we can derive from motion. He then considers the movement of a ball in reflection and in refraction. First of all, I doubt, and with reason it seems, whether the inclination toward motion must follow the same laws as motion itself, for there is as much difference between them as between potentiality and actuality. There you have my thoughts on these new propositions. I wish that the foundations upon which they have been established were better proven because the consequences he draws out from them when he treats the shapes that must be used for fabricating lenses are so beautiful, but I fear they may be as lacking of truth as they are lacking of proof.
Good. Thank you. Oh, get a sense maybe of Fermat's personality. Now let's get a sense of Descartes' personality. So we'll go to someone in the room this time. I see there's some people unmuting and raising your hands. I'm not sure if it's because you want to read or because you want to say something. Keep your hand up if you would like to. Well, maybe you can say in the chat, but the next reader is going to be from in the room here. So Descartes to Mersenne, October 5th, 1637. How does Descartes respond to Fermat's objections? Now, Mersenne, he's acting as sort of a go-between. You know, there wasn't any, this is sort of the equivalent back then of like an email thread. So you would send your letter to Mersenne, he'd copy it or have his assistants make copies and then send it out to other people. So one of them responds. So he sort of helped centralize this this exchange of views. So that's why they're both writing to Mersenne instead of each other, because they also know other people might be getting copies of these. Okay, so who's reading here in the room? Nancy, go for it. Maybe we can move that.
You've informed me that one of your friends who has read the dioptrics found some things objectionable. He has, first of all, doubted whether the inclination toward motion must follow the same laws as motion itself, for there is as much difference between them as between potentiality and actuality, end quote. But I'm convinced that he formed this doubt because he thought I had doubts about it myself. And because I included these words on page 8, line 24, quote, for it is quite easy to believe that the inclination to movement must follow the same laws as motion itself, end quote. He thought that by saying that something is easy to believe, I meant to say that it is only probable. In thinking this, he has strayed far from my intention, for I consider as practically false anything that is only plausible. And when I say that something is easy to believe, I do not mean that it is only probable, but rather that it is so clear and so evident that there is no need to bother myself with demonstrating it. 2, regarding what he says next, I do not at all understand his reasoning. I think I have made myself sufficiently understood by the comparison of the blind man's cane, by the comparison of the wine which falls through a vat.
Those are 2 other analogies in addition to tennis balls that Descartes used in explaining light. We didn't read all of it. Okay. Let's continue. Let's get one more back and forth of let's get 2 more letters by Fermat, actually. So go with an online reader. Margaret Chaldone's hand is up. Would you like to read, Margaret?
Yeah, sure. So this is Fermat to Mersenne in December of 1637. It says, my Reverend Father, in the letter of Monsieur Descartes that you took the trouble of sending me, I have seen the succinct responses that he made to the objections I raised against his dioptrics. I first must assure you that it is out of neither envy nor rivalry that I continue this little dispute, but only to discover the truth, an objective to which I think Monsieur Descartes will not be opposed, all the more since I know his very eminent merit, of which I make you a very explicit declaration. I will settle with a few words this dispute on reflection, about which I could say more, and prove that the author has accommodated his medium to his conclusion, of whose truth he was already certain.
That last, what does that last sentence mean?
Sure. I'll settle with a few words this dispute on reflection.
What does it mean? Could you restate what he's saying?
What? Ooh. I'm going to demonstrate here that Descartes actually rigged his experiment to support his preconceived conclusion.
He invented a medium to arrive at the right conclusion.
Right. So it's definitely a at least double entendre here. The medium, in other words, how does light move when it goes through some other substance? Or Descartes came up with this wacky explanation. But it was all to end up at that conclusion of whose truth he was already certain. Fermat is saying Descartes must have known the formula, and then he made up this ridiculous story to explain, oh, that's how I figured it out. This is my brilliant technique. Because this comes in a book, the Discourse on the Method of Conducting One's Reason Well, something like that is the title. Descartes wrote a book, here's how you think, how to think by me. And let me show you how I think about light. Look, I figured out how light bends. Descartes saying, Fermat says, well, maybe he knew this some other way. Maybe someone told him. Maybe he copied it. This is exactly what Leibniz ends up saying about Descartes. That he was in Leiden same time as Snell. That Snell figured this out. Descartes stole the idea and was the first one to get a book out on it.
Yeah, but he was wrong what he was saying about light, wasn't he? It could have been copying something wrong.
Well, the final formula is right. The final formula being that one horizontal line above is in a constant ratio to the one below, 4:3 for air and water.
Oh, he said that.
So yeah, Descartes arrives at that. We didn't get to it. We just read a little bit to see how his reasoning is. When he puts all this together, he ends up with that ratio. So maybe he knew that ratio some other way, just like people saw it and measured it and noted it down, and he made up this explanation because Fermat's not impressed with the explanation.
Common vernacular is.
Okay. Couple comments came online. Fermat is saying Descartes starts with an axiom or conclusion without really testing it. Yeah, in this case, he starts with both. He starts with his conclusion that he wants to get to, and then he uses a bunch of axioms that wind up at it. Axioms about tennis balls, blind man's canes, wine in a vat. So, okay, let's read one more. I think this is, oh yeah, so this is time for someone online. Stephanie, I see your hand is up. Let's come to you after we get someone in the room to read this next excerpt from Fermat. Go for it, Art.
Fermat to Mersenne, February 1638. My Reverend Father, I have learned by your letter my reply to Monsieur Descartes was not well received, and that he also raised objections to my method, maximus et minimus et tangentibus. Okay. I will not send you anything else for Monsieur Descartes, since he imposes such harsh rules on innocent discussion. I will content myself in telling you that I have yet to find anyone here who is not of my opinion, that his dioptrics has not been proven. I would only like to know whether people in Paris think he has given an exact demonstration of the foundations and the principles of refraction.
Okay. Now, yeah, this minimistic tangentibus, this is Fermat had come up with a general technique for. Fermat had come up with a general technique for finding where something was at a maximum or a minimum, a new way of finding tangents to curves. He used this to find tangents that Descartes said were impossible, that there was no way to find a tangent to certain curves, and Fermat did it. Descartes wasn't happy about this because he was extremely proud of his geometry book. And he did not like the idea that someone was saying he was wrong. I think we picked that up earlier from the kind of vibe he was conveying. He must have, maybe I didn't express myself with enough certainty, and that's why he thinks I doubted this. But really, it's true because, duh. Great explanation. Okay, so let's jump ahead now 20 years, and we will find out what inspired Fermat to come up with a new idea. So this, we're going to read this
kind of all the way through, if it's not all making sense, we are going to go through this on the whiteboard, but I think it's good to get the direct sources on these things. So we're going to continue with Marin Curo de la Chambre, and I believe it's time for an online reader.
I'll go ahead. Jason, if that's okay, Stephanie.
Go ahead. Yep.
Okay. Chapter 6 on the reflection of light. Why the angle of reflection is equal to that of incidence. It is a truth drawn from experience and disputed by no one that a reflected ray moves away from an opaque body in the same proportion that it fell upon it, such that it makes the same angle as that of incidence. This reflection is not, however, exclusive to light, for bodies reflect not only light in this way, but also sound and heat. And perhaps all the active qualities undergo the same movement. This is clear for sound, because an echo, which is nothing other than a reflected sound, can only be heard in the location that makes an equal angle with the first impression that the sound makes on a body. This being assumed, we must seek out the reason why reflections are made with equal angles. Nothing accords more closely with reason than their affirmation that the equality of angles in reflection is made in accordance with the laws that nature maintains in all its movements. For as it employs the shortest means in all its actions, it makes things move through the shortest space. It is certain that these lines make equal angles, for if impossibly the angles were not equal, these lines would not be the shortest. This can be demonstrated easily, I have to move something, easily by assuming that A is the ray which falls on the body B. I just lost the screen for a second. Hold on. Sorry. By assuming that A is the ray which falls on the body B and which is reflected at equal angles to C. For other lines terminating in these 2 points could not be drawn without being longer. For example, if A fell upon E and reflected to C, it is certain that these 2 lines, AE, EC, are longer than AB, BC.
Let's just take a second to repeat that last claim there. So he's saying light coming from A, here's the flashlight, here's where the light ends up going when it bounces off the mirror at B. He says, well, let's say that light bounced differently, and you could point the flashlight at E, and then it would bounce up to C. Why is that impossible? He's saying, well, because the path it actually takes, A, B, C, is a shorter distance, total distance, than path A, E, C. Therefore, the light can't bounce from E to C, but only at B. He's about to say why that's true. I just wanted to make sure that what he was claiming was restated. Okay, please continue.
By extending AB to D, making an extension of the same length as the reflected line BC, such that length ABD be equal to ABC, and also extending line AE to D, the extension ED having length EC, such that the length AED be equal to length AEC. It is evident that ABD is shorter than AED because together they make a triangle with ABD as its base and AEED the 2 legs. And in any such triangle, 2 legs are longer than the third. We see, therefore, by all this reasoning, that the equality of triangles in reflection is made along the shortest lines, and that this is not something particular to light, since nature observes the same order in all the movements that it causes.
I want to show a way that you can sort of show this geometric demonstration physically. All you need is a friend, a mirror. Well, it doesn't have to be a friend, another person, a mirror, and a string. So can we switch to that other camera? Okay, so you're really not going to be able to see this online very well. Oh, actually, we could if someone holds the, Jose, would you be so very kind as to stand here and hold this mirror bent? Okay, so you can kind of see that on online. I know it's
like that.
It's not that great. That is wonderful. Great. Good. And now, if I could have an assistant, please. Like
Martin.
Oh, Martin. Okay, that's a good idea. Martin got here early and we already practiced this, so. All right. So what we're going to do is hopefully it's kind of thick enough you can see it with the string. Again, this is something to do on your own too, just kind of tracing it out here. We're going to make that line A, B, C, and we'll see why the light doesn't bounce from A, E, C. So we're going to let our eyes be points A and C. So hold one end of the string at your eye. Or need a little bit more rope. Yeah. Okay. And then if we look for the place on the, Martin's going to put his finger on the mirror at the spot where he sees my eye. It's a little bit more difficult.
You want me to bend this more?
That makes it extra challenging. Okay. Yeah, now, can anybody in the room see, what, can anyone in the room see the reflection of these ropes?
Yeah.
Yeah.
If you look at the screen over there, you can
So
look at the cameras captured it.
does it look like each string is going in a straight line to the mirror image of the other person?
Yeah.
Does.
That's basically the proof that de la Chambre gave, is that when you look at when you consider the other person being within the, on the mirror side, going in a straight line to them, you just sort of flip it up and you end up getting equal angles. You can, if you try this, you can kind of push around the string and you can feel how, like, even if you start with your eye closed, you can just sort of feel the spot where you're able to get the most direct path. And then if you open your eye, you'll see, hey, I see the other person's eye. That's how reflection goes.
So using this or
That's it. Okay, good. Thank you. So.
How can you feel it without seeing it?
You know what? Let's do it after the, just because it's really not showing up well, and I kind of, but you and I will do it. All right, it's a date, Margaret. Okay. A couple other questions came in. Did Snell beat Fermat to the answer? What was he looking at? Yes. He beat Descartes and Fermat to the answer on light refraction. Who is Marin Curot de la Chambre? He was a physician in the royal court, and that's all I know about him. Yes.
What was Snell's explanation?
I don't know,
Oh.
because he never published it.
Oh, Snell. Okay.
So it's a little bit uncertain. I can just say for those who'd like to know more about this, if you take a look at the footnote on the bottom of page 9 in the handout, which we're not going to read, you get a fantastic quote from, okay, let's read it. It's really good. All right. Twisted my arm or whatever. Can anyone read I'm just going to read it. Here's the footnote on the bottom of page 9. This is a quote from Leibniz. It is known that Willibrord Snell, one of the greatest geometricians of his time, and well versed in the methods of the ancients, invented it, this formula, with having even written a work that was not published because of its author's death. But since he had taught it to his disciples, all appearances point to the conclusion that Descartes, who had come to Holland a little later, and who was most interested in this problem, learned it there. For the way in which Descartes has tried to explain the law of refraction by efficient causes or by the composition of directions in imitation of the reflection of bullets is extremely forced. It shows clearly that it is an afterthought adjusted somehow to the conclusion, which was not discovered by the method he gives. That's what Leibniz has to say. So now let's enjoy seeing what, so yeah, de la Chambre, light bounces at equal angles, not because the angles are supposed to be equal, but because nature is trying to do things the best way. And that's the shortest distance, the shortest path for the light. Okay, I think, I forget if we're, how about an online reader, I think. I'm not really keeping track very well. I'm going to raise a hand, especially, okay, Susan. And definitely, if you haven't read before, you're especially encouraged to please participate. Susan B., go for it.
So this is number, we're going back up, not past the footnote, correct?
We're going to read the end of de la Chambre's excerpt. This is on page 10 at the top, 67 to 68, it says.
Right. Can you put it back on the screen where it's large? Thank you. Okay. Therefore, anyone who considers Therefore, anyone who considers all these things well will doubtless judge that the first opinion that nature, quote, makes things move through the shortest space, end quote, is more reasonable than Descartes' explanation, which de la Chambre has summarized. For the principle upon which it is established is even more general and more in conformity with nature than all the others that have been put forward before it. Indeed, since nature does nothing in vain, it must take the shortest means to perform its actions, and it causes things to move through the shortest space and shortest lines. Therefore, it is necessary that nature performs all its movements by the shortest lines, and consequently, that it causes rays to reflect according to this general rule. Reflection being made thus, the angles in question must necessarily be equal. Nature does not have the goal of making these angles equal. Its entire plan is to go through the shortest lines, of which the equality of angles for these lines is a necessary consequence.
Okay, thank you. Let's read Fermat's response to this book from de la Chambre that he received. So someone in the room, please. Fermat passage on page 10.
I'll read it.
Thank you.
If you would permit me to join some of my geometry to your physics, we will accomplish a work of collaboration, which will put us first in defense against M. Descartes and all his friends. But since your principle served us well for reflection, can we derive some use from it for refraction? It seems to me that the thing is easy and that a little geometry will allow us to resolve the difficulty. I will not bother myself with refuting the demonstration of M. Descartes. It should therefore be sufficient to say on this account that M. Descartes has...
Please say Mr. or Monsieur if you want.
Monsieur.
They're very polite.
Okay, I'm sorry. Monsieur Descartes has proven nothing, and that I am in agreement with you in rejecting his ideas. But it is necessary to move on and find the reason for refraction in our common principle, which is that nature always acts along the shortest and easiest path. It seems at first that this could not succeed, and that you yourself have made an objection which appears invincible. For since on page 315 of your book, the two lines CB
BA, which contain the angle of incidence and that of refraction, are longer than the straight line ADC, which forms the base of triangle ABC, it follows that the ray from C to A, which traverses a shorter path than that of the two lines CBBA, should, in accordance with our principle, be the sole and true root of nature, but which nevertheless is contrary to experience. But we can easily extricate ourselves from this difficulty by assuming with you and with all those who have treated this matter that the resistance of the media is different, and that there's always a certain ratio or proportion between those two resistances when the two media have particular consistencies and are internally uniform.
You state what he's on this diagram here. This is from de la Chambre's book, a part that we didn't read. De la Chambre says, well, least distance really seems like a great thing, but not when light bends. Because if you shine the light from A to B, it bends and comes towards C, but clearly the shortest distance would have been to go in a straight line. And light didn't go in a straight line, it bent. So I guess something's wrong here. I don't know how to explain this. So, but Fermat is about to try doing that. Go ahead.
Let there be then, for example, in your figure, the ray CB
changes media at point B, where it deflects to reach point A. If these two media were the same, the resistance to the passage of the ray along line CB
Louder.
would be to the resistance of the passage of the ray along line BA, as line CB is to line BA. Or were the media the same, the resistance to light's passage was the same in each of them. And consequently, the ratio of the traversed spaces would remain the same.
From which it follows that since the two media are different, and consequently
The resistance is different.
one can no longer say that the resistance to the passage of the ray along the line CB will be to the resistance along line BA, as line CB is to line BA. But in this case, the resistance along line CB will be to the resistance along BA, as CB is to another line, whose ratio to the line BA will express the ratio between the different resistances.
He's about to give an example that is very general. So let's.
For example,
if resistance through medium A is double resistance through medium C, then the resistance along CB will be to the resistance along BA, as CB is to double BA. And if the resistance through medium C is double the resistance through medium A, then the resistance along CB will be to the resistance along BA, as CB is to half BA. So in these two cases, the two resistances along CB and BA being combined can be expressed as either CB plus half of BA or as CB plus twice BA.
Okay. So let's look on the picture here. So let's say it's twice as hard to go through the water in gray as it is to go through the air. Fermat's saying we don't want the shortest distance, we want the least resistance, the path of least resistance. So you take length AB, and then you add double the length BC, because it's hard to move through this. He's saying if you do that, AB plus twice BC actually is shorter. There's less resistance than if it went on a straight line. Because the straight line, overall distance is less, but look, the distance within the hard to move through medium is longer. CD is longer than CB. And because you go so much slower in it, it's actually more efficient to go a little longer in the air and a little bit less in the water. And there's some sweet spot where, you know, because if you go too far, if you say, oh, let me go over here and then straight down, now it's good. The time's going to start getting the distance. resistance will get worse. So this is the least resistance path. That's with the double and so forth. Yeah, you can skip one paragraph and jump to if we suppose that point B.
Okay.
If we suppose that point B has been found and that nature acts always
along the shortest and easiest path, the resistance along CB added to the resistance along BA will contain the sum of the two resistances. And this sum, in compliance with the principle, must be the least of all those sums which could be created at any point along line DB.
Okay. Then let's jump to the point B which will be found.
The point B, which will be found by the construction of this problem, will be the point where the refraction will take place. I confess to you that this is not one of the easiest problems, but since nature solves it in all refractions in order not to depart from its ordinary way of operating, why may we not tackle it? I guarantee you in advance that I will find the solution whenever you like.
So why is Fermat saying he's going to find the solution later? Didn't he already find it?
Well, he hasn't talked about time yet.
Well, it's true. He's in this case he's referring to it as the least resistance. What's the problem that he says he'll solve later when de la Chambre asks him to?
How to find exactly where B is?
How to find exactly where B is. Right. So you know it's not going to go in a straight line, but exactly how far over should you move that point to get the least distance, at least resistance. So, okay, so Fermat, at this point, he has an idea that light takes the path of, Fermat has the idea that light takes the path of least resistance, but he doesn't have an angle for light yet where he could check and see, is this right? Descartes has this explanation, Fermat's got a different explanation. Is Fermat right? Is Descartes? Well, it's hard to tell by doing any observations if you don't have from Fermat some specific prediction to test. So at this point, he doesn't have that. There's a letter from Fermat to a Cartesian, which we'll skip, and we will go ahead to this letter from 1662 to de la Chambre. And this will, I think, be the last thing that we're going to definitely read together. So I believe we are on Zoom. Is there a Zoom volunteer to read Fermat's letter to de la Chambre on page 12?
Yep, I can do that.
Okay, please do.
Sir, it is right to obey you and to finally bring to an end, through your intervention, the old dispute that has long existed between Mr. Descartes and me on the subject of refraction. Perhaps I may be fortunate enough to propose a piece that you will find advantageous for both parties. I told you previously in my first letter that Mr. Descartes has never demonstrated his principle, for aside from the fact that comparisons can scarcely serve as the basis for demonstrations, he employs his in the wrong way and even assumes that light's travel is easier through denser bodies than through rarer ones, which is plainly false. To escape this predicament and to try to find the true reason of refraction, I indicated to you in my letter that if we wish to employ in this study the very common and well-established, I've reached the end. Do you want to move it up? Thank you. I'm sorry. To escape this predicament and to try to find the true reason of refraction, I indicated to you in my letter that if we wish to employ in this study the very common and well-established principle that nature always acts by the shortest paths, we will easily benefit from it. But first of all, because you have raised the objection that nature, in directing light along the two legs of a triangle, could never act by a path as short as if it had moved along the base, I set out with an easy example to cause you to see the opposite of your thought, or rather of your uncertainty. Let there be circle ACBG with diameter AOB, center O, and another diameter GOC. Okay, needs to be moved up. From the points G and C, let there be drawn perpendiculars GH, CD onto the first diameter. Let us suppose that the first diameter, AOB, separates the two different media, of which the lower of the two, AGB, is denser and the upper, ACB, rarer. Let it be rarer to such a degree that, for example, passage through the rarer medium is twice as easy as passage through the denser. From this assumption, it follows that the time expended by the body in motion or by light to go from C to O is less than that taken to go from O to G, and that the time of movement from C to O made in the rarer medium is only half the time of the movement from O to G. Consequently, the measure of the entire movement of the two lines, CO and OG, can be represented by adding half of CO to the full length OG. Similarly, if you take another point, such as the F, I've lost the place again. Where was I? Now assume that the radius CO is 10 and consequently that the total diameter COG will be 20. Assume that line HO is 8 and line OD will be 8 as well. And finally assume that line OF will have a length of 1. I say that in this case, the movement along line COG will be made in a longer time than the motion along the two sides of the triangle CFFG. For if we prove that half CO plus OG is greater than half CF plus FG, the conclusion will be clear. Since these two sums are the precise measures of the times of these two movements, now the sum of half CO with OG is exactly 15, and it is obvious by the construction that the line CF is equal to the square root of 117, and that FG is equal to the square root of 85. But half of the first root added to the second is less than 59 over 4, and 59 over 4 is less than 15. Thus the sum of half CF with FG is less than the sum of half CO with OG, and therefore the movement along the lines CFFG, shall I continue? Is made more quickly and in less time than the movement along the base COG.
Okay, let's take a second. I'd encourage people who have this printed out or on your own paper to fill in these numbers that he's giving. Let's get one of these square roots so that we can feel that we're doing a bit of doing what he's saying here. Yeah. Okay, so I'm gonna switch and draw this here. Oops. Okay. Can you oh, this isn't showing up, is it? You can't see the circle that I'm drawing?
No, well, I can't.
Okay. Well, that's a shame. Do it on the board. That's why we have a board, isn't it? Okay.
Is that one?
To write on.
Watch the buttons.
So,
Buttons.
Can anyone say why is Fermat, what's he doing? Why is he getting these numbers and so forth?
Hold on.
What's his point?
Okay.
Why is Fermat doing this?
Can you?
What's up?
Nothing. We just want to make sure Zoom can see it too, because I care about them.
Oh,
I think if we turn, oh,
you can.
Use the better camera.
No,
I don't know how to adjust this thing now.
Well,
and
the,
if we turn off the ceiling lights, we can also see.
This knob right here, it's listening.
first off, we're not even seeing it.
I was just gonna do this well.
Oh, I see.
Oh.
Maybe you can just hold it for this part. Well, it's hard to adjust.
keep going. And then just
You can also
Perfect.
tilt it. Perfect. Good. Wonderful. Okay. So so here's the now. So what's Fermat doing? Why is he drawing this diagram and making these lengths? Anybody say?
Well,
Okay. So light doesn't go from when light goes from air into water, it does not move on a straight line. It does not go COG. It comes from C over to F and then it bends down to G. Why? Fermat says it's because there's less resistance if it goes through point F. How do you know that? So he's saying, well, let's do this. Let's, in each of these cases, so the radius of the circle is 10. The resistance, he says, you take half of the distance up top because it's so much easier to go through the upper medium, and you add it to the distance below because it's harder to go through that medium. So what's the total resistance of the path COG if it's half as hard to move through the air? 15. Yeah. So we take half of CO, the length is 10, but the resistance is only 5 because it's easy. OG, the length, and the resistance is 10. So he says, let's say that this, what did he say? He says, let H.
Can you say why that again?
F will have a length of 1. And then he says, GH has a, oh, and he says that this length is 8. This is 6. So let's figure out the distance. What's this one? All right, so I've just labeled what he said. How long is line CF? How do we figure out how long line CF is? What geometrical tool can help us figure out a line whose length we don't know? Okay, CF is the hypotenuse of a triangle.
Yes.
Yeah, that's a good point. Let's take a look at this triangle.
Okay.
Here, here, here.
Where did the 6 come in? I don't get that.
You're right. I totally just skipped that. Let's get the 6 first. Thank you. Okay, so Fermat says that this length is 8. So let's use the Pythagorean theorem on this triangle, which will maybe we could prove some other time.
3, 4, 5. Okay.
What do we know about this length on a triangle? We know that if we draw squares on 2 of the sides, well, we don't know. We've heard. Maybe we'll know in the future.
We should prove Pythagoras theorem first, and then
maybe we should. It's worth actually going through whether this is true or not. Because, okay, so these 2 areas make up this one. Let's go with that for now. So here, this side is 8. What's the area of its square? 64. 64. What's the area of the square on the hypotenuse here?
100.
10 times 10 is 100. So we need to make 100. We've got 64 so far. How much more do we need to add?
Oh, we need a
36.
36. And is conveniently, is there a square whose side is a nice number that gives us? Yes. Yeah.
Oh,
All right. So that's where that 6 comes from.
Oh.
Thank you for keeping me honest. Okay. So now let's take a look at, we'll take line CF. Let's see if we can say how long it is. So CF, Pythagorean theorem again. So this is one side. What's the area here? What's the area? What's this square?
36.
36. Then what's this distance here? It's 9. We got 8, and then Fermat just said this is what?
Right, so it's 9.
It's 9. So let's do 9 squared plus 6 squared. What do we got?
117.
81 plus 36.
It's 117.
117. So that's why Fermat says that the length of line CF is the square root of 117.
Okay.
0.81.
How about FG? Let's get FG.
Well, can't we just do the same thing we did up there on the knee?
Sure. Yeah. So what will be the squares on the 2 legs here for this triangle?
Well, that would be 36, right?
36.
Yeah. And then would it also be the same 9? Right?
No.
No, it would be
7.
7, yeah.
Yeah.
49. 36.
Yeah. What do we get if we add those? 36 plus 49. How much does that come out to?
85.
Carry a 1, 85. So this length is the square root of 85. I think that's what Fermat said. So now, since we conveniently have someone with a calculator, which is a big plus, what is half of the square root of 117? Because remember, it's easier to move up here. So we only take half the distance, measure the resistance. What's half the square root of 117 plus the square root of 85?
It doesn't do square root.
Half of it. The square root would be 5.4. Right.
Just checking it. There's a few things coming in on the chat.
I just do square root of 117 divided by 2.
Yes, that's right. Oh, there's some really interesting comments on the chat. So I'll read those when we come back together here.
Is this right?
For what?
Square root, half of the square root of 117.
Sounds reasonable.
Okay.
Is it
5.4083269?
Okay. So 1/2 the square root of 117 is about 5.41. All right. What's the square root of 85?
9.2195.
9.22, let's say. So half of the square root of 117 plus square root of 85. We add these two numbers.
14.60.
14.63. So that's less than 15, isn't it?
Yeah.
So Fermat said, hey, for sure, if you want to take the path of least resistance, it's not a straight line, and the resistance changes. Okay, so let's keep going and then see what he does with that. Okay. So we left on. So we're on page. We're on the top of page 13. I think it's time for a reader in the room. Oh, yes. Okay. I'm going to read a few of these comments and then we'll get to the thrilling conclusion Fermat comes to. Nancy says, let's not lose the forest for the trees. Our amazing universe is ordered in such a way that light knows, in advance no less, the pathway that will bring it from one point to another across 2 or more media in the least time. Am I the only one astonished by this undeniable reality?
How did you know that?
Well, because it can't be denied.
it's so clear and no. Oh, true. We don't know for sure that it's undeniable yet.
Why even demonstrate?
But isn't that it's true? This is an astonishing hypothesis. The idea that light knows how to choose a path of least resistance. How does it know? Is it measuring? Is it carrying around a calculator? Look how long it took us to figure this thing out. And it's got to do it every time it's moving from one medium to another. That's tough.
Speed of light. Also,
yeah, it's got to do it at the speed of light, right? It's in a hurry. Yeah.
The fact that we chose the point C and G, and then we had to find the point like F. Whereas in reality, if you're pointing a laser, you choose F, and then nature figures out where it actually goes. So I think that makes it a little hard to get your head around.
Okay, that's a good point, Adrian. I'll just for make sure, I'm just going to repeat it. That in the diagram, we when we're pointing our laser, we're already saying where point F is because that's where we're pointing the laser.
Right. That's
so
okay.
it's more like how do you find where G is? Like where is it going to bend to down there? So this kind of diagram seems a little counterintuitive to the way we would actually try to solve the problem.
Well, couldn't you just like get like a physical tank or something, and then shine a laser in it, and then actually do it?
Yeah. But so then the question is like, okay, we know where C and F are. Where's G? Where do we put G down here? Where does it refract to?
Which at the end of the. Well, go ahead, Matt.
You put it. That like this model, it doesn't even make sense to even have like a line of COG then, right? Because it's just.
Yeah.
Fermat's
point here isn't that he knows he's not demonstrating. He's not saying that F is the best place.
Yeah.
He's just saying it's better than
yeah.
It's better than going in a straight line.
Okay.
He's still going to come to how do you find where F should be?
But I like what Adrian is saying is that like thinking of like having this line of COG or like thinking of it in that way doesn't even make sense in the first place to already think that line goes or that light goes in a straight line if you're already making point F.
Right. He doesn't think that light might actually go in COG. He's using the diagram to say if it did, it would have taken more time. There would have been more resistance. So
we can physically demonstrate it if you chose a target G, and then you took a string from G to your laser, and then you point the laser at G and see where the red light appears on the surface of the water.
Or you figure out where do you point the laser, where is F, so that it ends up at G.
Right.
Yeah.
That's right.
Yep. Let me read. There's a couple more comments. Let me read these, and then we'll keep reading because we got to hear what Fermat says. Morrigan, I hate to leave. It's getting interesting, but I need to run. Descartes is always very humorous to read, and people arguing against his ideas. Very interesting. See you next time. Religious and don't we already have a tank? Yes, we do. CK, Jason, how did he arrive at half of the resistance and not another fraction? That's a good question. So Fermat, when he used 1/2 in this example, he's not saying that that's the actual ratio. He's just throwing out some number. His point so far has only been to say that the shortest distance is not necessarily the least resistance or the least time. That's a good question. Does the fact that sound moves faster in water than in air, does this challenge Fermat's theories? Interesting question. So you would, maybe it does, maybe it doesn't. We got to figure out which way sound refracts when it enters water. Which way does it bend? So that would be something for that. Okay, so let's keep reading and find out from Fermat how do we find point F? So I think we're on the room. Yeah. Someone in the room. It's your turn to read at the very top of page 13, number 4. This will be the last reading today. Is there a volunteer from the room, please? Hi, Reiner.
I don't want to have to start making chicken noises. Okay. Oh. Push me the button.
Oh, okay. I arrived at this point without much difficulty, but it was necessary to take the study further because to satisfy my principle, it is not sufficient to have found a point such as F through which the natural movement is made more quickly, easily, and in less time than along the straight line COG. We must find the point along line AB that allows the journey to be made in the least time possible. For this, it was necessary to have recourse to my method of maxima and minima, which quite successfully solves this sort of question. As soon as I attempted to take up this analysis, I had two obstacles to surmount. The first was that although I was sure of the truth of my principle, which is that there is nothing as probable or apparent as the assumption that nature always acts by the easiest means, which is to say either along the shortest lines when time is not a consideration, or in any case by the shortest time in order to complete its work and to achieve its ends quickly. Nevertheless, I was advised on all sides, and principally by Monsieur Petit, for whom I have the utmost respect, that the experiments accord precisely with the proportion of refraction that Monsieur Descartes has given, and that although his demonstration is faulty, I feared that it would be useless for me to attempt to introduce a proportion different from his, and that the experiments which would be made after I had published my invention would be able to destroy it on the spot.
Can you restate that? What's his difficulty? What's he concerned about?
He doesn't want to just assert something which has been observed, and it's observed that what Descartes has, the principle, the ratio is correct, but he wants to propose a solution which won't change that, so that it won't be by somebody else set up an experiment and they say, no, but see, you were wrong.
Right. Yeah, Fermat is a different idea than Descartes, so the observations match Descartes, so
what do we do?
Exactly, make it very confident that we're right. Okay, go ahead, please.
The second obstacle to my study was the length and the difficulty of the calculations, which in the solution of the problem that I mentioned in my letter and which I showed you was not so easy. I freed myself from the first obstacle by my knowledge that there are an infinite number of proportions different from the true one, which approach it so closely that they could fool the most able and exact observers.
Okay, there's a lot of so would anyone like to verbalize that? What's the and aha here?
The footnote might help. Should we read it or no?
That kind of gives it away.
Yeah.
Words. And it's okay if you read it, but just say in your own words. If you said please, why? Oh.
Oh, no one made a
Okay, I guess I was hearing things. Okay. Well,
should I read the footnote now? For those who didn't,
sure. Okay.
We couldn't hear their so.
Because of what Adrian did.
Good.
I see.
Suzanne says, she said because of what Adrian did last week. Exactly. Let's get the footnote, Matt. Go ahead.
Johannes Kepler, considering a similar question, writes in chapter 21 of his 1609 Astronomia Nova, there are, however, occasions upon which a false hypothesis can simulate truth within the limits of observational precision. Pierre Hergon writes of Kepler in his Cursus Mathematicae, work that Fermat refers to in the postscript of this letter, and with which he was therefore familiar. Hergon, Kepler, the wisest of modern astronomers, did not accept any kind of hypothesis that saves appearances, but wanted simple hypotheses in accord with physical cause.
Kepler wasn't a secret. It was a popular math textbook that also published Fermat's method, and that's what they had to say about Kepler there. So just the historical connection. Okay, please continue.
Therefore, having only the second obstacle to vanquish, and I'll repeat that, was the length and difficulty of the calculations, I had often resolved to employ the well-loved geometry, as Plutarch calls it, to convince you and to satisfy myself as well. But the apprehension of finding after a laborious and painful operation some irregular or fantastic proportion, and my natural inclination to laziness, left things in this state up until the most recent remonstration that Monsieur le Président de Miremont delivered to me on your behalf, which I took as a law stronger than either my apprehension or my laziness. And so I resolved to follow your counsel without further delay. I therefore proceeded at once, by virtue of obedience, as the monks say, in carrying out your orders, and I worked out the whole analysis according to my method. But the reward of my work was the most extraordinary, the most unforeseen, and the happiest that could be. For after having run through all the equations, multiplications, antitheses, and other operations of my method, and having at last solved the problem, as you will see on a separate sheet, I found that my principle gave exactly and precisely the same proportion of refraction that Monsieur Descartes had established. I was so surprised by such an unexpected outcome that I had difficulty coming out of my state of astonishment. I repeated my algebraic operations many times, and the result was always the same, even though my demonstration assumes that the passage of light through the dense bodies is more retarded than through rare ones, an assumption which I find quite true and indisputable, and yet Monsieur Descartes assumed the contrary. What must we conclude from all this? Would it not suffice, sir, for the friends of Monsieur Descartes, that I leave him in free possession of his theorem? Will he not have enough glory in having known the actions of nature at first glance and without the aid of any demonstration? I even add in favor of Descartes that it seems that this great truth of nature did not dare to stand up against his great genius, and that it let itself be taken and discovered by him without being forced to do so by demonstration. Like a fortified location, which, although otherwise strong and not easily conquered, nonetheless surrenders based solely on the reputation of the attackers, without even waiting for the cannon to fire.
So that was supposedly a compliment to Descartes. Very exciting. Let's read one more. I know I said that was the last, but I forgot. We have to get the Cartesian response to Fermat's principle. So pretty. Now, just to put the timeline on this, it was 1657 when he wrote that light takes the path of least resistance. This letter, where he actually found what angle that will make, he wrote on New Year's Day, 1662. So when he said he was lazy, maybe he's not kidding. It took him over 4 years to do the work on that. Okay. Yes.
I'm sorry, but he also, when exactly does he say least time instead of least resistance?
Oh, he says least time in this letter.
In the 62.
Yeah, he also says least time in 57. I used excerpts.
Okay.
Because part of the reason he says resistance is that de la Chambre does not believe that light takes any time to move.
Okay.
So he's like, okay, well, if you don't like time, have resistance.
But he's already thinking time.
Fermat is thinking and saying time.
Right. Okay.
Yeah. Okay. And now something very interesting from one of the questions that came up in the chat. No one had measured the speed of light, and that wasn't going to happen for like one or maybe even the better part of 2 centuries, right? So no one's ever measured it. But Descartes has one hypothesis. It goes faster in water. Fermat says it goes slower. Who does history judge to be correct? The answer is Fermat.
Science.
The science. Uh-oh, I know the science. Okay. Did I say that really?
No,
Oh my God. Oh, okay. All right.
It's like you got to understand,
Okay.
So Descartes didn't have the advantage of, the insight that was given us all because Newton invented gravity. They didn't have gravity before then. It hadn't been invented.
I see. Okay, here's another comment, and then we'll get this nasty quote from Cartesian. Eugene, I guess. Hugues writes, truth, light has always been there. It is our hypothesis, our question. The angle of the mirror perception, refraction, where we are standing from the light, the mirror, our own personal previous knowledge, experience, and well-being, information gathering, source, quality of measurement, author, that will produce a certain outcome, our own perception refraction. The Earth has magnetic anomalies, Bangui, South Atlantic. What I'm trying to say is that as humans, we tend to think we can use how things behave on Earth to try and explain the universe. Although conditions might be different, the amount of humidity in the air, different gases, different gravity. Okay. I think we are now ready for it. Yes.
I was sort of running through this experiment in my mind. If you view this experiment from the point of view of a light particle, would it, well, it would probably not perceive like a difference, sort of like what we talked about last week about like a body orbiting in a highly elliptical orbit with a apogee and perigee, which are very different. It would also not perceive an acceleration, even though in regard to the body it is orbiting, it would change its speeds constantly. So I was thinking about that, from the point of view of this light energy or wave or particle, it would probably not care. It would not perceive sort of this difference. I was thinking of like trying to view it from a different perspective, sort of like Einstein would do. But I haven't found the answer yet. But I was just throwing it out there.
Fantastic hypothesis. As a matter of fact, this is actually very literally something that Einstein did. Is that he said, he took the general principle of least action, least time, has become essentially the most universal principle of physics. You can basically express all physics laws in terms of least action.
Yeah.
At least they're all consistent with it. For Einstein, light goes in a straight line. And if we did this thing that we did with the rope here, where we saw in the mirror and it looked like the rope was just a straight line between one of us and the mirror image version of the other, if we did something similar, like in water, if we had a really still surface and you get the rope and figure out where in the water so that you see the person's eye here. If we did that same kind of thing, it would look like a straight line from the person in, either person, it would look like a straight line. So yeah, light is it bending? Is the space changing?
A philosophical question.
And it's a very different approach because for Descartes, every time the light gets to a new medium, something has to either break through a cloth or get whacked by a tennis racket. Fermat, principles everywhere. It's nothing special happens when you enter a new medium. I mean, something happens, but principle isn't something that occurs at that spot.
Yep.
It's bigger and smaller. Okay. Not everyone liked what Fermat had to say. So would someone on Zoom please volunteer to read a short response from Claude Claircellier? Claircellier was essentially Descartes' intellectual heir. Descartes was dead by this time. And he was compiling the collected works of Descartes and so forth. And of course, defending Descartes against anyone who thought that there was anything that he didn't know. Would anybody on Zoom like to read? You've got 5 seconds to raise your hand, or we'll go with someone. Rachel, okay.
The principle that serves as foundation for your demonstration, namely that nature always acts by way of the shortest and simplest paths, is but a moral principle and not at all physical, which is not and could not be the cause of any effect of nature. It is not a physical principle because it is not this moral principle that makes nature act, but rather the secret force and the virtue that is in all things, which is never driven to a particular effect by this principle, but instead by the force which is in all causes, which converge together in a single action, and by the disposition found in all the bodies upon which this force acts. Yeah. And it could not be the cause of any effect of nature, because otherwise we would assume nature to have knowledge. And by nature, here we mean only that order and that law established in the world as it is, which acts without foreknowledge, without choice, and by a necessary determination. The same principle must put nature in an unresolved state, not knowing what to do when a ray of light passes from a rare body into a denser one. Because I ask you, if it is true that nature must always act by the shortest and simplest pathways, and since the straight line is undoubtedly both the shortest and the simplest of all, then when a ray of light has to travel from a point in a rare medium to a point in a dense medium, is it not the case that nature must hesitate? For if you wish nature to act by the principle of following a straight line immediately after the break, then isn't your path the shortest in time, while the straight line is shorter and simpler in measure? Who will decide then, and who will give a verdict on this matter? Since time is not what moves things, it also cannot be that which determines movement. This pathway, which you claim to be the shortest, because it is the quickest, is only a pathway to error and confusion, a pathway that nature does not follow, and could not have the intention of following. For since nature is determined in everything it does, it never tries to direct its movements along anything but straight lines.
Can I say something?
Please, Jose. What's up?
He does raise a good question, but I had in reading some of Fermat, he said that nature always acts by the easiest means. It's like, well, how does he define nature? Because I thought, if he's talking about light, I could accept that, like light always, but what does he mean when he says nature? It seems like everybody here has some pre-established notion of nature that I'm just not catching up on. And then one thing that this hater says here on Vermont is like, he says, and it could not be the cause of any effect of nature because otherwise we would assume nature to have knowledge. It's like, yeah, why are we assuming that nature would have knowledge? Doesn't Lynn in the beginning, which I highlighted, by the way, because I wanted to ask about this in the beginning, but you said no, because we had to keep reading. Knowledge is always essentially subjective because it exists among mortal beings only as human knowledge. Primary existence lies consequently only within the human individual and that individual's functional relationship to the history of society within which he or she lives. Knowledge in the proper sense of the word does not exist among lower forms of life. So I just think there's maybe, I don't know if I'm getting caught up in semantics, definitions, or what, but it's like what do they mean by nature, and what do they mean by nature having knowledge or intention? Yeah.
Fantastic question. Anyone want to weigh in on this?
It's only a centuries long discussion, so you can,
I think.
That might go. Yeah.
Oh, come on.
Yeah, that might go.
No, I mean, I like the idea of intention, which is inherent, couldn't be inherent in nature, like baked into the cake of it, and they don't, natural creatures might not know about it.
I've seen deer run in front of cars.
Yeah.
So
just sort of running on
They want to
instinct.
provide dinner.
But was it a straight one? Oh.
Jason? Jason, can you hear me?
I can, but let Mike finish first, please.
Oh, okay. Go ahead, Roger.
The gentleman yields. Go ahead, Roger.
Okay. I had a bit of a revelation watching your video, which if people haven't watched it, I highly encourage them to do. When you made the connection at the end to economic policy. And for some reason, I had never quite thought of this connection before. But we always talk about how the future has to determine our present actions, that we have to think about where we want to move society to, and from that standpoint, determine what we as active participants in the here and now must do to bring that about. And I was trying to think about this from a Vernadskian standpoint, that while these are different domains, that in some way fundamental principles must be consistent and coherent between those different realms. And in the same way that we as living active human beings can think about what our intention is, where do we want to be in the future, that somehow that must be reflected in these lower domains. And I was thinking perhaps in the biotic domain, that's represented by evolution, where organisms don't consciously think, what new species do I want to evolve to become? But yet that is a physical force in nature that does occur. We do evolve, we do come to higher platforms, and perhaps this principle of least action is something akin to that reflected in the abiotic domain, where it's not literally knowledge of where the beam of light is going to go, but somehow the physical universe is still organized such that that occurs, that the light does take the path of least action, whether it's consciously doing that or not. That's the way the physical universe exists. And that somehow that principle of maximizing action exists in all of those different domains. So that's what I thought about after watching your video.
Well, I want to return to Jose's question on. So you said a couple things. What do we mean by nature? What does nature mean to us? It's funny, the way Claire Cellier is scolding Fermat, he says, how does nature act? By the way, nature only acts from each. It's like in the Republic when Socrates is making fun of Thrasymachus, and he's saying, it's like you're asking me, what is 12? But don't go telling me it's 6 times 2 or 3 times 4 or anything like that. Like he's ruling out the potential of, he's saying what nature can do, and maybe Fermat figured out something new about a better way to think about nature. So does light actually think about it? I don't think so. And I don't think Fermat thought so either. I don't think that he believes that light is conscious or figuring out what it's going to do. He's saying that nature is doing this. So, in other words, the way nature causes light to move fulfills this condition.
Okay.
One really helpful distinction on this is one that Leibniz comes to this in the Discourse on Metaphysics. And he says, well, what's the difference between a final cause and an efficient cause? Sometimes you've got an overall cause, but still moment to moment, there's also an efficient cause. And you really can think about both of them. They're both real. So for example, later Huygens, with his wave theory of light, he gave a efficient cause of why light bends when it goes into a new medium. He said, here's what's happening right at that boundary. waves are doing this thing, and then now it's coming out at a different angle. So Leibniz doesn't think one's right and one's wrong. Leibniz doesn't say, I got to choose between Huygens' wave theory and Fermat's least time. They're both true. But one of them is in the domain of, I think he says, one of them is like in the domain of power, and one of them is in the domain of wisdom or knowledge. I forget how he puts it. So the wave and all this is what happens. This is how nature makes it occur. But still, why did nature or God do something in a certain way rather than another way?
Right.
So,
no, I mean, it does help because then it's like, then you think about light as kind of in the same sort of principle and domain of like why a honeybee makes a hexagon, the shape that's most efficient, right? And that light is not outside of these kinds of, way of intention, basically, right? So see, from that standpoint, then I can understand why light is a part of nature.
I really like your example of the bees. Are the bees, I mean, do they have little compasses and protractors? When they're making these hexagons, they're not thinking about, filling, that's just, they do what they do.
Yeah.
But there's some other broader process, kind of like what Roger was getting at in nature, that they do the best thing.
Just add to that a little bit.
Yes, and then we'll go to, there's a couple people online that have their hands.
Real quick, just in line with what Roger was saying, if you think about just the way a plant grows, and the plant will seek light, maximize its intake of light for photosynthesis. It's an intention. Right?
Oh yeah, like how does a plant know or trees know to like move this way? Because there's more sun here.
Yeah,
right.
Exactly.
Like my money tree that's dying right now is like trying to
Okay, there you go.
get through the window.
Problem with money theory, right?
Wait. But I think your question was, how does that apply to the abiotic domain? A little bit, it's harder to understand, right?
Are you going to answer that, or are you just going to pose it?
No, I think you guys were.
Oh, okay.
Let's see, there's a couple more thoughts here. But yeah, so just again to reiterate that the discourse on metaphysics is a great thing to read on this.
Okay.
Leibniz is real concise on this topic. Milton writes, until 1920, it was believed that the number of planets in our solar system was fixed, and a new planet was discovered. Should we seek new hypotheses to reveal what lies hidden? Yes, definitely. And I think that makes me think of what you picked out here, Jose, about knowledge always being subjective, or knowledge existing among mortal beings only as human knowledge, connected to your relationship to the history of society. Yeah, anything that we know is always provisional. This is what we got from the first class with Plato and Nicholas of Cusa. Everything's a surmise. You have a hypothesis. You can say that it's right in a certain way, but it's always subject to being overturned later, refined later. You never know any part of the truth so perfectly that it couldn't be better known. Okay, Jerry had a hand raised, but then put it down. So
Gretchen had.
yeah. So and then Gretchen was the next to put her hand up. So let's go with Gretchen.
Well, you began to get at it, what I was thinking of when you were answering. I mean, but much more specifically when you answered Jose. But in your video, again, another plug for the video. When the section you got to before you went to economy, where you, as I recall it, right? Because I before that I was sort of, I don't know what, banging my head against. It's like, yeah, but really, how does nature have an intention? You know, how you sort of get into fixed mindset. And when you began talking about the way, anyway, what I got out of the next thing when you began, you can't break down a process. Okay, this happens in this part and this happens in the other part, and you add up the two parts and then you get to what's happening. We have to constantly be going for what is the larger process of which it is a part, which is what you really did in answering Jose there about saying what is nature anyway. And it was funny. It was as if like my mind shifted. I mean, it was really suddenly I saw, I was looking at it before, like trying to grab hold of it, something, rather than just stepping back and thinking how this whole thing could work. I don't know if that adds anything to it, but I do recommend the video. It's and then the economic part reinforced what you were saying of how intentional.
Well, I can't disagree with you. I think it was a pretty good video. Yeah. Joel, you're unmuted. Would you like to say something? Joel, did you mean to unmute?
They did measure the speed of light by looking at the moons of Jupiter. I only 76. So light knows it has a speed limit.
Light has a speed limit?
How does it know the speed limit?
No, you were saying a couple centuries to make light. No, only Romer who and Leibniz in Paris measured the speed of light in 1676.
Okay. Yeah, okay, so that was just short. That's true. That was just shortly after Fermat. That was yeah, it measured it astronomically. So sometime when Jupiter was far from the Earth, the moons would, because Jupiter's moons go behind Jupiter, you can't see them, and then they pop out. And you can write down like exactly what day and time did someone first see the Mars appear on the other side. And people notice that, wait a minute, when Jupiter is far away from us, the moons are kind of late. They're not showing up when we think they ought to show up. Are they changing their speed based on how close they are to us? And what Romer had hypothesized, he said, well, no, the light's taking some time to move. And that delay isn't because the moon was late, it's because the light took some time to get to us. And so he was actually able to give a measurement, an estimate of the speed of light. And that was well before people, did it in a lab and got exactly the exact speed. There were, okay, I realized I'd missed some other comments that came in here. Julian is asking for a comment on his earlier comment on the Theaetetus. Let me find that, make sure. Or was this, oh, I'm sorry, this was that, Milton? Oh yeah, Julian. Okay, so here's a question that came in online. Comment. Jason, at some point, would you please answer, at the end, the conclusion of Plato's Theaetetus, Socrates says, knowledge is neither perception nor true judgment, nor an account added to true judgment. Well then, our art of midwifery tells us that all of these offspring are wind eggs and not worth bringing up. Would you like to add to this for the class or cite other quotes from Plato? So what you're referring to there is that Socrates, this was, I think, right judgment. Another way it gets translated is right opinion. So Socrates really distinguishes between knowing something and having the right opinion. So you might have a belief that's not wrong, but you still don't know it. Today, we use the Pythagorean theorem. I think many of us, at least at some point, didn't know whether that theorem is true or not, because no one bothers to teach it in school. They just say this is true and use it. So we might have the right opinion about the Pythagorean theorem without knowledge about it. Okay, let's, okay, this is lightning round now. So 2 or 3 minutes tops. Richard Freeman, Laney, and anyone here can jump in between.
Okay, I think the video that you did, Jason, was wonderful. So I don't know if a consensus will mean that it's true, but I think we're getting pretty close to that. I just wanted to introduce one idea, which is something you and I have discussed, which is that the universe is generated and ruled by the principle, or governed by the principle of noesis, of the principle of creative cognition, even before man appears.
It's a principle that's always been eternally self-developing in the self-developing universe. And that governs both the biotic and the abiotic, although the abiotic and biotic are not conscious of that principle. And that's why I think if you shift, just to respond to what Jose was saying, if we shift to know that that's true, and I think it's provable, I'm not going to do it here, then you know that nature acts according to not to the least action or least time principle, and the most efficient principle, as Leibniz would say, but that is the principle of nature. The assumption that, what's his name, Claire Cellier introduces, which is what we're all taught in school, is that nature is dumb and it only really reacts to physical things bumping into one another or other things like that. And then we try and figure out, well, how from that can we make that coherent? I think if you begin from the assumption that nature is not dumb and it's governed by noesis, then these things are very natural. And Claire Cellier says, well, that's a moral principle. You could call it a metaphysical principle, but it's true. And it takes a shift of the mind to see what science really is. That's it.
Okay, thank you. Lainey, you please go ahead and unmute.
So coming up from Richard, but I had some other very brief idea. Schiller actually very much works on the idea of nature and how to live with it in a productive way, I'll put it. So anyway, it would be too much to talk about. But concerning intention, and sorry for not putting my picture on, but my face is tilted, so it looks ridiculous. So Lynn said when most of the older members were in our 20s, he said, you have to think about that you are 70 years old and then live your life accordingly. And I remember when I was in my 20s, I thought, oh my God, that's difficult to think about that I'm 70 when you are in your 20s. But think about that you're 70 years old now and direct your life accordingly. Then he upped the ante when he wrote the preface to Amelia Boyden Robinson's autobiography, where he said, you have to think about that you've been dead for 50 years. And then think about, have your life been worthwhile living? What did you do with your life? So that's concerning how human beings can consciously, like Lynn tried to get us to do, have an intention that then makes the path of your life. That's what I wanted to say.
Right. Does your life have an intention? So, okay, let's bring in the close one. We're gonna wrap up now. Let me give a few concluding thoughts. We're over time about what's coming up on Wednesday and on Sunday. So we talked a lot about purpose today, intention. This came up, Jose was asking about it, Claire Cellier hates the idea, obviously, he's totally opposed to it. Bertrand Russell said that purpose was an idea that's scientifically useless. Isaac Newton said, I don't do hypotheses. So when he said that gravitation was a mutual force between corporeal bodies, he said, so why does that happen? I don't know. That's really not my job. I'll leave that to, I don't make hypotheses. I just call it like I see it and I tell you what I see. So the idea of intention is extremely controversial. I mentioned that least time became a very universal principle. So least action is a sort of more refined form of least time that incorporates least time for light, but also applies to mechanics, electromagnetism, basically everything. And this principle was later developed by Hamilton, William Rowan Hamilton, and others. And wait, yeah. And it now is the central principle. So Fermat's legacy was not to know with certainty what angle light bends at. I mean, it's true, but the real profound significance of this is that it gave a different idea of what kinds of things could be a cause. The idea that a final cause actually can be something that you can use to know the universe better, which we do now with least action. So he was absolutely right on that. On Wednesday, we were going to answer the question that Fermat posed and we didn't really get to today, which was how do you find point F? So on Wednesday, we're going to look at Fermat's method of maxima and minima and apply it to the resistance of light, find the exact path that has the least resistance, and we'll recreate with him his steps where he ends up getting Descartes' formula at the end. That's for this Wednesday. Next week, Leibniz, the infinitesimal. So that was well introduced by Lynn in the excerpt that we began the class with today. And there'll be some reading available for that, hopefully on Tuesday. And Leibniz is such a gem. So I would really encourage you, make some time during the week, like plan if you can put some time aside Thursday, Friday, Saturday. Set aside an hour to read some of the Leibniz in advance. It'll really, it's very enriching.
Where is everything
Thank you.
archived, Jason? Where's everything archived?
You can find this class and all the others on the class website at larouche.info/science. The discussion sessions on Wednesday are not posted on the website, but if you are registered for the classes, you will have received that in an email sent straight to your inbox. If you're not registered for the classes, please do, and then you'll get the links for the discussion sessions, which are not posted. We always stream live on YouTube, and the video is available immediately after the class. So you'll already find this video on the class website. Okay, so thank you, everybody. Thanks for the participation. Really appreciate the level of comment and dialogue.
Thank you.
All right.
Cookies.
Enjoy your weekend.